All right, so my name is Stephan Jackowski, and today I'm going to be talking about the research I've been doing with Dr. Shi the past 3 semesters on the electrochemical deposition of aluminum-doped zinc oxide. So first off, zinc oxide is a group 2,6 semiconductor with a hexagonal crystal structure here. As you can see, the 6 sides. Some advantages of it are that it's a direct band gap semiconductor of a band gap of around 3.37 EVs at room temperature. It has a high electron mobility, and it is capable of alloying with magnesium and aluminum. When you introduce aluminum, you get aluminum-doped zinc oxide, and it has a optoelectronic application as a low-cost, transparent conductive oxide. These are found in solar cells and LCDs as like the top contact for a solar cell, so you can bring light. They're transparent, and they also conduct electricity. The most commonly used one right now is ITO, 10-doped indium oxide, and the problem with that is that indium is very scarce, so it's very expensive. So for our sample preparation, we use a silicon substrate of resistivity 0.01 ohm centimeters. First, we clean it in an ultrasonic methanol bath, followed by chemical etching with 0.25 molar hydrofluoric acid. For our back contact, we use sputter-coated gold palladium, and we applied a seeding layer of spin-coated zinc oxide nanoparticles. These are for the growing of thin films because the aluminum and zinc ions don't like to really stick very well to the silicon, so we need this seeding layer just to grow them. After the nanoparticles were spin-coated, we annealed the sample for 10 minutes at 150 degrees Celsius, and we repeated this process over and over again to make sure it was a good seeding layer. So for the characterization methods, we used an SEM, so a scanning electron microscope, to study the morphology of the film. We also used an energy dispersive X-ray spectrometer to quantitatively analyze of the elemental concentration. We used an X-ray diffractometer to study the crystal structure, and a photoluminescence spectrometer to measure the band gap. So here's the experimental setup. We have a DC power supply, which in our case is a constant current source in series with the resistor and the chemical cell. The anode is a platinum wire, so when the chemical solution is ionized, these zinc and aluminum positive ions will be attracted to the negative station right here, which is where the silicon substrate is. We monitor the voltage across the cell using this interface and a computer. So for the electrochemical deposition, the solution contains zinc nitrate, aluminum nitrate, hexamethylene tetramine, which I'll call HMT for obvious reasons, and 40 milliliters of DI water. We fix the HMT concentration at 20 millimolar, and we vary the zinc nitrate and the aluminum nitrate in the solution. But overall, this total solution of aluminum and zinc is held constant at 20 millimolar, the same as the HMT. The advantages of this electrochemical deposition method is that it's low cost, very low temperature, and we have the ability to change several parameters such as the current, the voltage, the solution concentration, temperature, and time. For our case, we're only changing solution concentration and keeping everything else the same. So just for a control, this is an SEM image of pure zinc oxide. So we're going to try to characterize zinc oxide before introducing any aluminum to the solution. So these, you can see a very random arrangement of all these little like rod or needle-like structures, but it's fairly uniform in terms of its density across the board. And just for an idea of scale, this is 30 microns right here, so the whole thing is close to 100 microns. So if you cut a piece of at it, it's about basically a human hair would fit on this whole entire screen right here. As we zoom in a little closer, this is a 10 micron scale right now. You can kind of see these rod or needle-like structures, which are interesting structures, so we can compare it later to the aluminum-doped zinc oxide. As for the EDX, this is for the elemental concentration. We expected to see zinc oxide and silicon because that's the substrate. But we do see this little peak right here from aluminum. And what we did to make sure that wasn't a part of the film, it was only part of the substrate, we analyzed the substrate as well. We see the same exact little peak right here from aluminum, saying that the aluminum was a part of the substrate and actually not a part of the film. So we can eliminate that, and we got everything we really wanted. So the XRD, we get these peaks here indicating there are several peaks, so it's polycrystalline structure. And then for the PL spectroscopy, we have a peak here, the UV emission peak at 375 nanometers, which is about 3 EVs. And which is slightly lower than the 3.37 EVs that were expected for just zinc oxide. Remember, that was at room temperature, and this is at 20 Kelvin. We also see this yellow band emission right here, which is characteristic of zinc oxide due to some impurities. So the real question is, what happens when we introduce aluminum into the solution? What kind of changes are we going to see? So as you can see here, at a 1-to-1 ratio of zinc to aluminum in the solution, we see this really beautiful array of aluminum doped zinc oxide nanowires. With this, you can actually see the hexagonal crystal structure. And each one of these, this is a scale of 5 microns. So each one of these is about 1/100th of a human hair. As we increase the aluminum concentration from 1 to 3, we see basically that we're kind of losing some of these. They're becoming more of like rod or corn-like structures or flower-like structures, and they're kind of dissipating. We're getting this two-dimensional flaky film surrounding it. As we increase the aluminum even more, we basically see no more of these rod-like structures, and it's all mostly a 2D flaky film. When analyzing the EDX of all the samples, we normalized it to zinc because all we really want to know is how the aluminum is changing and not really how the zinc is changing. We just want to know how the aluminum is changing if we normalize to zinc. And as you can see here, as we increase the aluminum, we get in the solution, we get an increase in aluminum in the film. This is the XRD of the sample. So these are arbitrary units, so these are all just kind of shifted down. But what you can get from this is that each peak is smaller as you increase the aluminum concentration, indicating that the crystal structure is degrading as we increase the aluminum. There's one exception to that, and that's the 1-to-1 sample, the nanowires. So we're going to look at that a little closer. So you see this peak right here. Preferably, it's increasing the crystal structure in the 002 orientation, and this is because the nanowires are perpendicular to the substrate, and they're all very uniform. So any XRD that we get off of that is going to be in that direction. And here's a photoluminescence spectroscopy of all the samples. First, you can see right here that the yellow band emission, the top one is the zinc oxide, and the lower ones, the colored ones, are the aluminum. So we reduce the yellow band emission by incorporating aluminum into the solution. And then also there's a slight peak right here, as we've blown it up right here, with the 1 to 3 ratio. We never really looked into that, but it's something to look at in the future. And then also, you can see that we got the peak, our UV peak at a 1 to 3 ratio, but we've lost our 1-to-1 ratio peak. It's somewhere redshifted. So what we try to do is we're trying to recover this UV peak, and what we did was we annealed the sample at 350 degrees Celsius for 30 minutes in air, and we see that we recovered this peak. The one before was the red one before was a 1 to 3 ratio. This one is just a 1-to-1 annealed. So after annealing it, we recover this peak, and that's exactly what we wanted. So now that's all great, and we showed that we can incorporate aluminum into the zinc oxide through this method. But it's on silicon, and its real application is in like transparent conductive oxide. So let's put it on something that's transparent. And a good example of that is ITO on glass. And I said that ITO is expensive and it's really rare, but as long as it's a thin enough layer, it's not all that expensive, and it has a lot of positives about it. It's transparent substrate. It requires no back contact or sheeting layer or chemical etching, and this just increases all the sample preparation time. It makes it a lot faster to do. And the sample prep for the other, for silicon is around an hour, and this only takes 3 minutes to clean an ultrasonic methanol bath. The deposition time is also minimized to 5 minutes, and instead of having a constant current source, we have a constant voltage of 3 volts across the cell, and we monitor the current to make sure that there's continuity in the cell. The morphology of the zinc oxide and ITO has changed, obviously. Before it was a bunch of random little needles and rods. And now it's more like beads, or it almost looks like the formation of those nanorods, or like the corn-like structures, but it's more beads and kind of a random. The PL data for this actually here is the UV emission for the laser. It's a 355 nanometer YAG laser. And so we don't actually have a peak here. This is just from the laser, and we see that there's this yellow band emission. So for aluminum, it's actually higher than the zinc oxide, which is different than from before. And what we try to do is we try to, once again, like recover these UV peaks. And what we did was we annealed the sample again at 350 degrees for 20 minutes, and we see that we recovered both of these peaks. And actually, after the annealing, we have reduced the yellow emission for the aluminum doped zinc oxide as opposed to the zinc oxide. In summary, the introduction of aluminum to the solution, with the exception of the 1-to-1 sample, directly affects the aluminum concentration in the films. It changes the morphology. It degrades the sample as identified by the XRD, and contributes to a slight luminescence in the 400 to 450 nanometer regime. In the 1-to-1 sample, we showed that there's a hexagonal nanowired array, an improvement in crystal orientation, preferably in the 002 orientation, and a decrease in UV emission after the annealing process, or an increased UV emission after the annealing process. As grown zinc oxide is usually an insulator, but adding aluminum could increase the conductivity for optoelectronic applications and could cause a redshift in the band gap. And that's it. Thanks to Hunter Shi and the Department of Physics here.